I'm all right. Do you guys have questions from homeworks or anything before we get started here? I see if you have questions from homework before we get started. No? Okie dokie then. The plan today is very much similar to the plan from yesterday. We'll do like 35 or 40 minutes of stuff, give you the homework assignment, give you the rest of the class to work on as these things stack up here pretty quickly. We have a bunch of stuff's due, so I don't want to just keep plowing forward full speed ahead. Everybody cool with that? Okay. Just as a fair warning, seniors, we are now entering into content that I would say you are not responsible for. So just keep that in mind. What we're going to be doing today is we're going to be looking at some real-world situations that can be described using logarithmic or exponential equations, and then doing some examples of solving those sort of situations. So sound or sound intensity is a situation that can be described or has a logarithmic relationship. So we say that the sound intensity in decibels is given by the formula beta equals 10 times log of I over I naught, where beta is the number of decibels, I is the sound intensity measured in watts per meter squared, and I naught is a constant, which is basically the threshold of human hearing, i.e. like what's the quietest sound that a person can hear. So, for example, any situation that's kind of involving sound, the way I'm going to write my equation is going to be using this model, and then we'll just be solving. So given the sound intensity of a busy city traffic is approximately 10 to the negative 15 watts per meter squared, so this is like my I. What is the measure of the city traffic in decibels? What we're looking for then is the beta. So I'm just going to plug this in. And I naught is always this constant. Hello. I have Paige Maralinga, not Reese.
Wrong Maralinga. Okay.
Yeah.
Jackson Broadway.
That's okay. Paige, tell your sister happy birthday. Okay. So again, I'm just going to drop in that constant for I naught. Any sound problem we're using, that constant is the same. And then it's just calculator time, my dudes. I know, right? Like, let's just calculator party. So I have 10 to the negative 5th divided by 10 to the negative 12th. And we get 70 decibels. Sweet. No big deal, right? The next example is like earthquakes. Anyway, with like the decibel stuff, you guys know what a decibel is, right? Like when you're watching a sporting event or whatever and the crowd's really into it, they oftentimes have the little like sound meter on the screen that's like, oh, it's 80 decibels in there. It's like the sound of a plane taking off or something, you know, like the announcers like to talk about that kind of thing. And the next one we'll talk about is the Richter scale. That's how we measure earthquakes, like the severity of an earthquake. Earth science people are probably familiar with the Richter scale. So the magnitude of the earthquake, R, can be found using the equation R equals log of alpha divided by T plus B, where alpha is the amplitude of the vertical ground motion at the position of the earthquake. So like how much up and down the ground is moving. T is the period. So that's like how long it goes from the ground to move up, move down, and then return to its starting position, like when we're talking about like a sine or cosine wave. And we measure that T in time, so that's like in seconds. And then B is a constant. So ideally, when we measure an earthquake, to get the best measurement possible, we want our measurement tool to be at like the epicenter of the earthquake. Can we predict where earthquakes are going to occur? Not really. So is our equipment at the epicenter every time there's an earthquake? Not really. What do we know about earthquakes? As you get further and further from that epicenter, then the severity of the earthquake's effects decrease, right? So this B at the end, this constant, is just basically a fudge factor for like how far away our instrument was from that earthquake. So that would have been something the scientists would have calculated empirically based on like collected datas and be like, oh, you're this far away and you measured it as this, and this one is this far away, measured that, and this one is this far away, measured that. And you can use those measurements to kind of come up with, okay, as we get further and further away, the intensity decreases by this kind of factor, and we just tack it on. So that's what the B is. Does that make sense as to what that is representing? Everybody's excited. So the do an example here. So it says the infamous San Francisco earthquake had a Richter scale magnitude of 7.5. How many times more severe was the most severe earthquake ever reported? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So this is kind of a tricky one. So we're given 2 Richter scale measurements, and it doesn't seem like we have a lot else, right? So with this, I can say that like 7.5 is going to equal the log of like alpha 1 over T1 plus B1. Bless you. And then R2 will say kind of the same thing, except we have some 2's here. So we're kind of making like a system of 2 equations, right? Before I start in on that, though, what are we trying to look for? I'm looking for how many times more severe was the most severe earthquake. So of our measurements, alpha, T, and B, the one that's going to be talking about the severity is going to be like that vertical ground displacement, right? The more up and down movement you're going, the more rocking and rolling the ground is doing, the more severe the damage is going to be, like buildings falling over and all that kind of stuff, right? So what we're looking for is what is the quotient of A2 over A1 equal? Right? That's going to tell us how many times more severe A2 was, or earthquake 2 was than earthquake 1. Does that make sense as to what we're looking for? Notice it didn't actually ask for the severity of one earthquake or the other earthquake. It wanted a ratio of the two. So that's going to help enormously. So my plan here is I'm going to take R2 and subtract R1 from it. So far, so good. So this is just going to be 9.5 minus 7.5, or just 2. Now what we're going to do is we'll distribute that negative sign through. And we're going to think a little bit about what's going on. So this value for B, this is like our correction factor, right? That correction factor, because we've 9.5 and 7.5, those measurements already have a correction factor attached to it. We can just kind of assume that those two correction factors can cancel out, right? So the 9.5 and the 7.5 already basically have a correction factor of 0 attached to them, because we're not taking a raw measurement from it. So we can just kind of cancel those out. Well, that's lovely. So what I'm left with now is a difference of two logarithms, right? I can use the quotient property to rewrite that and condense those two logarithms. And I remember that dividing a fraction is the same as multiplying by the reciprocal. Everybody's okay with that? Now, I know we live in Michigan, and probably none of us have ever witnessed an earthquake, but on an earthquake, the period, the ground moves up, moves down, returns back to normal. Do you think that happens? How fast do you think that happens? Really fast, right? Like if the ground is shaking, it's like really going, right? It's probably happening so fast that the difference between the T1 and T2s is almost negligible. So we're just going to kind of assume that they'll just cancel each other out, that they're basically the same number, because the ground rocking is happening so fast that like there's probably not a big difference between the two. Okay. So all we need to do now is just cancel out that logarithm, and we're going to have what we're looking for, the A2 divided by A1. What do I need to do to cancel out that logarithm? What cancels out a logarithm? It's not a logarithm doesn't cancel a logarithm. It's the other one, the exponent base. So what is the base of this logarithm here? Because that's the same base of exponent I want to use. I don't see a number down there. What number is there if we just write log with no number there? 10, yes. So we're going to use exponent base 10 to both sides. And here's me drawing my comically big 10s again. So that I have the ratio of A2 to A1 is 100. So what that's saying is the Chilean earthquake was 100 times more severe than the San Francisco earthquake. Ooh, that's bad. So the takeaway here is that each whole number difference in the Richter scale is a factor of 10 difference in severity. So like a magnitude 4 earthquake is 10 times as bad as a magnitude 3 earthquake. And a magnitude 7 earthquake is 10 to the 4th, like 10,000 times as bad as a magnitude 3 earthquake. Right? So every difference in one is a factor of 10. Woo, buddy. I'm glad we live in Michigan. We don't have to worry about this. Although I have been in an earthquake in Michigan. So for a while I lived in like the very southwest corner of Michigan. And there was like I think it was like a 5 something earthquake in like northern Illinois. And I could feel it. I was sleeping in my bed like Saturday morning or something. And I'm like, this is shaking a little bit. Like it was very subtle, but like could feel it. And then like a day later, I heard on the news about the earthquake in northern Illinois. I'm like, oh, it was Saturday morning. That's what that was. Like I didn't even put it together when it was happening till I heard about the earthquake later on. I'm like, oh, okay then. So that's my story. Another situation that can be described using an exponential logarithmic function is pH. So those of you that have been in a chemistry class or maybe are currently in a chemistry class know a little bit about pH. It's how we measure the acidity of a substance. So our formula, the pH is equal to the negative log of the concentration of hydrogen ions in a compound. So this little symbol here, when you put the brackets around a element with a plus or minus on it, you're talking about the ion, and the brackets around it are the concentration of. These are all like chemical terms that you don't really need to know. The example says a really sour lemon is found to have a pH of 2.2, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two items? So my pH for the lemon is going to be, I'm just going to label it this way, lemon. So the pH is 2.2. So to get the concentration of hydrogen by itself, I need to start by getting that negative sign to the other side, so I can like divide by a -1. And then I need to cancel out that logarithm attached to the concentration of hydrogen ions. What cancels out log? Exponent base 10. Just like last time. So, pew pew. So there's my answer. I could turn that into a decimal if I wish. I don't wish to, though. And then the other thing was some bleach. There the pH was 10.2. So we set it up the same way. And we do the same algebra. Can I skip down to the answer? Because it's going to be like the exact same process. Skip the work. We're going to get 10 to the negative 10.2. That's my bleach. And part B says how many times greater is the hydrogen ion concentration of the bleach than the lemon? That's a typo because the bleach has way less hydrogen ions than the lemon. So we're going to do, if we want to know how many times greater it is, we're going to do the concentration of the lemon over the concentration of the bleach. So that's 10 to the negative 2.2 over 10 to the negative 10.2. And I guess I could do this without a calculator. I'm going to do it with the calculator, though, because I expect that's probably the way most of you guys would want to do this. Thanks, bud. And holy smokes! Nope. I have 4, 5, 6, 7, 8, 9 zeros, I think, on that one. That's 10 to the 8th. Woo, buddy, that's a lot more hydrogen ions. So again, a difference in 1 pH means a factor of 10 change in the hydrogen ion concentration. And we got one more situation to talk about. Sound good to you guys?
Good.
Yeah, it's so exciting. The last thing we're going to talk about is called Newton's law of cooling. So when you decide to get a job as like a medieval blacksmith for the summer, this will become particularly helpful to you. So Newton's law of cooling describes how like objects that have been heated up cool down. So the T of T is our temperature of the heated object at some future time T. The Tm is the temperature of the surrounding medium. So like if it's cooling in air, it's the temperature of the room. If it's like, if you're taking a hot sword and like annealing it, like plunging it into cold water, it'd be the temperature of the water. Hi, Mr. Whalen. You looking for somebody?
Just checking.
Oh, okay.
But yeah.
You, okay. You know, if it's a, you know, you took your hot, you know, like, or even could be like, you take your can of soda from the store and you put it in the refrigerator. Be the temperature of the refrigerator would be the medium. Everybody's okay with that? And then the T naught is the initial temperature of the heated object. So like if it's your can of soda, it'd be like probably room temperature is what I'd assume the can of soda's at. You know, if it's your sword as your blacksmithing, it would have been like whatever the temperature of the furnace was that you were heating it up in, and then before you pounded away on it. You know, if it's your cookies that you baked in the oven that you set on the window ledge to cool, it'd be the temperature of the oven was the initial temperature of the cookies, you know. And then the last thing here, we have this value K. K is a constant that's specific to the substance that you're heating. So that constant for iron, like if you're a medieval blacksmith, is going to be different than your constant for your soda pop, which would be different than your constant for your cookies. It's all specific to the substance that you're heating or cooling. Does everybody feel okay about what the values are representing? Because that's going to be maybe the trickiest part of the story problem, is getting things in the right place, right? Because you got to read the situation, be like, okay, that's a TM, that's a T naught, that's a TT, that's a constant. All right. So let's do a situation here. It says a hard-boiled egg is heated to 96 degrees Celsius. It's placed in a pot of water 16 degrees Celsius to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. How long will it take to cool the egg to a temperature of 20 degrees Celsius? So I see a whole bunch of temperatures in here, right? What don't I see at any point, or what don't I hear in this at any point? I don't hear a K, right? That should be really easy to pick out if they've given me a K, right? Because we're not told a constant for anything in here. So sounds like my first step is going to be to figure out K. So far, so good. Now, to do that, we're going to need everything but K. So we're going to need a T of T, a TM, a T naught, and a T, right? We need all the other parameters to do that. So let's start reading this. And I think probably the easiest one to pick out to start is going to be that initial temperature. So what should our initial temperature be here? (96) to be the temperature of the eggs before they start cooling, right? Everybody feel good about that? Okay. Next, let's find the temperature of the medium. What is the temperature of the stuff the eggs are cooling in? 16, right? That's how cold the temperature of that pot of water that we're cooling things in. Okay. What's the temperature, or what's the time, the future time that we're given? 4 minutes. Oops. And the temperature at that future time is 45. Everybody feel good? So now I'm going to go ahead and plug these numbers into my formula. So I have 45 equals 16 plus 96 minus 16 e to the negative k times 4. So now I'm going to solve for k. So we'll subtract 16 from both sides. Again, the goal is to get that exponential piece by itself, right? So 45 minus 19 is 29. Or I'm sorry, minus 16 is 29. 96 minus 16, that's just 80. So I'll divide both sides now by 80. I could make that a decimal, but I'm not going to bother making it into a decimal because it's just going to go into my calculator at some point anyway. So now the exponential part is by itself. How do I cancel out that exponential base of e? I need to use a logarithm, and the specific logarithm I need is the natural logarithm, which is log base e. That's correct. So do the natural log of both sides. And then I'll just divide both sides by -4, or I'm going to think about it typing into my calculator as multiplying by -1/4. But now it's just calculator time. It's our favorite time of the day. Yay, calculators! You'll never let me down, Mr. Calculator, until you run out of batteries in the middle of the big test. Ugh. So I get about 0.254. Now we can do the next step of our problem. The last thing it's asking me in the problem then is how long it will take to cool to 20 degrees. So how long it's asking for a little t, right? So we're going to need then a t of t, a t naught, a tm, and a k. Well, we have our t naught, that was 96. We have our tm, that was 16. We just found our k, that was 0.254. That future temperature that we need is the 20 degrees. And so what do? We just set up our equation one more time. Everybody feel okay? And now it's basically the same algebraic steps, right? We'll subtract 16 from both sides. And we'll divide by 80. Again, I recognize that that fraction can reduce, but who cares? It's just going to go into my calculator anyway. We'll do the natural log of both sides. And then we'll just divide by -0.254, or I'm going to just write it as multiplying by the reciprocal. And look at this, I have the full unreduced number in my calculator, so I'm going to take that. So -1 over ans times the natural log of 4 over 80. So I have about 11.8 minutes. And there you go. So on any of these cooling problems, if you're not given a K, that's probably your first order of business is to figure out what the K is. And then we'll go ahead and answer the core part of our question. All right. That's it for me. Do you guys have any questions before we break? So for the problem set that's due right before break, we're going to start that 131 to 138. That's not a big deal. And then we'll have a delta math next week. And then on the X day, basically just like a homework catch-up day, because we've had a million homework assignments and a lot of problems due. And this is just a chance for us to slow down and get some stuff done before we leave for break. Maybe try to clear our slate so we don't have anything due. It's all done and taken care of. That would be most excellent. But that's it for me, guys. Everybody cool as to what's due when? So Sunday's problem set is going to be what is like 38 through a million. And then we have a delta math number 1 should be done by now, I would think, but if you haven't finished that, you'll want to try to make sure you get that done. But those are the two things I'll be looking for Sunday, like 38 through 130. Oh my God. And then the delta math. But again, you've had, like a bunch of time this week in class to work on stuff. So I'm trying to be considerate on that.